warm up the engine without engaging the rotor. Freewheeling unit. Since lift in a helicopter is provided by rotating airfoils, these airfoils must be free to rotate if the engine fails. The freewheeling unit automatically disengages the engine from the main rotor when engine RPM is less than main rotor RPM. This allows the main rotor and tail rotor to continue turning at normal in-flight speeds. The most common freewheeling unit assembly consists of a one-way drag clutch located between the engine and main rotor transmission. This is 236. Usually in the upper pulley in a piston helicopter, or mounted on the accessory gearbox in a turbine helicopter. When the engine is driving the rotor, inclined surfaces in the drag clutch force rollers against an outer drum. This prevents the engine from exceeding transmission RPM. If the engine fails, the rollers move inward, allowing the outer drum to exceed the speed of the inner portion. The transmission can then exceed the speed of the engine. In this condition, engine speed is less than that of the drive system, and the helicopter is in an autorotative state. Airplane assembly and rigging. The primary assembly of a type certificated aircraft is normally performed by the manufacturer at the factory. The assembly includes putting together the major components, such as the fuselage, empennage, wing sections, nacelles, landing gear, and installing the power plant. Attached to the wing and empennage are primary flight control surfaces including ailerons, elevators, and rudder. Additionally, installation of auxiliary flight control surfaces may include wing flaps, spoilers, speed brakes, slats, and leading edge flaps. The assembly of other aircraft outside of a manufacturer's facility is usually limited to smaller size and experimental amateur-built aircraft. Typically, after a major overhaul, repair, or alteration, the reassembly of an aircraft may include reattaching wings to the fuselage, balancing of and installation of flight control surfaces, installation of the landing gear, and installation of the power plant rebalancing of control surfaces. This section is presented for familiarization purposes only. Explicit instructions for the balancing of control surfaces are given in the manufacturer's service and overhaul manuals for the specific aircraft and must be followed closely. Anytime repairs on the control surface add weight fore or aft of the hinge center line, the control surface must be rebalanced. When an aircraft is repainted, the balance of the control surfaces must be checked. Any control surface that is out of balance is unstable and does not remain in a streamlined position during normal flight. For example, an aileron that is trailing edge heavy moves down when the wing deflects upward, and up when the wing deflects downward. Such a condition can cause unexpected and violent maneuvers of the aircraft. In extreme cases, fluttering and buffeting may develop to a degree that could cause the complete loss of the aircraft. Rebalancing a control surface concerns both static and dynamic balance. A control surface that is statically balanced is also dynamically balanced. Static balance. Static balance is the tendency of an object to remain stationary when supported from its own CG. There are two ways in which a control surface may be out of static balance. They are called underbalance and overbalance. When a control surface is mounted on a balanced stand, a downward travel of the trailing edge below the horizontal position indicates underbalance. Some manufacturers indicate this condition with a ++ sign. An upward movement of the trailing edge above the horizontal position indicates overbalance. This is designated by a - sign. These signs show the need for more or less weight in the correct area to achieve a balanced control surface, as shown in figure 260. A tail-heavy condition static underbalance causes undesirable flight performance and is not usually allowed. Better flight operations are gained by nose-heavy static overbalance. Most manufacturers advocate the existence of nose-heavy control surfaces. Chord line. Tail down underbalance. Plus open parent plus closed parent condition. Chord line. Nose down overbalance. Minus open parent closed parent condition. Chord line. Level horizontal position. Balance condition. Figure 260. Control surface static balance. 237. Dynamic balance. Dynamic balance is that condition in a rotating body wherein all rotating forces are balanced within themselves, so that no vibration is produced while the body is in motion. Dynamic balance as related to control surfaces is an effort to maintain balance when the control surface is submitted to movement on the aircraft in flight. It involves the placing of weights in the correct location along the span of the surfaces. The location of the weights are, in most cases, forward of the hinge center line. Rebalancing procedures. Repairs to a control surface or its tabs generally increase the weight aft of the hinge center line, requiring static rebalancing of the control surface system, as well as the tabs. Control surfaces to be rebalanced should be removed from the aircraft and supported, from their own points, on a suitable stand, jig, or fixture. Figure 261. Trim tabs on the surface should be secured in the neutral position when the control surface is mounted on the stand. The stand must be level and be located in an area free of air currents. The control surface must be permitted to rotate freely about the hinge points without binding. Balance condition is determined by the behavior of the trailing edge when the surface is suspended from its hinge points. Any excessive friction would result in a false reaction as to the overbalance or underbalance of the surface. When installing the control surface in the standard jig, a neutral position should be established with the chord line of the surface in a horizontal position. Use a bubble protractor to determine the neutral position before continuing balancing procedures. Figure 262. Hinge center line bubble protractor. Support stand. Chord line. Figure 262. Establishing a neutral position of the control surface. Sometimes a visual check is all that is needed to determine whether the surface is balanced or unbalanced. Any trim tabs or other assemblies that are to remain on the surface during balancing procedures should be in place. If any assemblies or parts must be removed before balancing, they should be removed. Rebalancing methods. Several methods of balancing rebalancing control surfaces are in use by the various manufacturers of aircraft. The most common are the calculation method, scale method, and the balance beam method. The calculation method of balancing a control surface has one advantage over the other methods, in that it can be performed without removing the surface from the aircraft. In using the calculation method, the weight of the material from the repair area and the weight of the materials used to accomplish the repair must be known. Subtract the weight removed from the weight added to get the resulting net gain in the amount added to the surface. The distance from the hinge center line to the center of the repair area is then measured in inches. Is. Inboard hinge fitting. Outboard hinge fitting. Figure 261. Locally fabricated balancing fixture. 238. Distance must be determined to the nearest 100th of an inch. Figure 263. The next step is to multiply the distance times the net weight of the repair. This results in an inch-pounds in LB answer. If the NLB result of the calculations is within specified tolerances, the control surface is considered balanced. If it is not within specified limits, consult the manufacturer's service manuals for the needed weights, material to use for weights, design for manufacture, and installation locations for addition of the weights. The scale method of balancing a control surface requires the use of a scale that is graduated in hundredths of a pound. A support stand and balancing jigs for the surface are also required. Figure 264 illustrates a control surface mounted for rebalancing purposes. Use of the scale method requires the removal of the control surface from the aircraft. The balance beam method is used by the Cessna and Piper aircraft companies. This method requires that a specialized tool be locally fabricated. The manufacturer's maintenance manual provides specific instructions and dimensions to fabricate the tool. Once the control surface is placed on level supports, the weight required to balance the surface is established by moving the sliding weight on the beam. The maintenance manual indicates where the balance point should be. If the surface is found to be out of tolerance, the manual explains where to place weight to bring it into tolerance. Aircraft manufacturers use different materials to balance control surfaces, the most common being lead or steel. Larger aircraft manufacturers may use depleted uranium because it has a heavier mass than lead. This allows the counterweights to be made smaller and still retain the same weight. Specific safety precautions must be observed when handling counterweights of depleted uranium because it is radioactive. The manufacturer's maintenance manual and service instructions must be followed, and all precautions observed when handling the weights. Center of repair area measurement in inches. Hinge center line. Chord line. Figure 263. Calculation method measurement. Mounting bracket. Trim tab. Rudder. Bubble protractor hinge center line. Adjustable support. Support stand. Weight scale. Figure 264. Balancing setup. Aircraft rigging. Aircraft rigging involves the adjustment and travel of movable flight controls which are attached to aircraft major surfaces, such as wings and vertical and horizontal stabilizers. Ailerons are attached to the wings, elevators are attached to the horizontal stabilizer, and the rudder is attached to the vertical stabilizer. Rigging involves setting cable tension, adjusting travel limits of flight controls, and setting travel stops. In addition to the flight controls, rigging is also performed on various components to include engine controls, flight deck controls, and retractable landing gear component parts. Rigging also includes the safetying of the attaching hardware using various types of cotter pins, lock nuts, or safety wire. Rigging specifications. Type certificate data sheet. The type certificate data sheet TCDS is a formal description of an aircraft, engine, or propeller. It is issued by the Federal Aviation Administration (FAA) when the FAA determines that the product meets the applicable requirements for certification under 14 CFR. It lists the limitations of information required for type certification, including airspeed limits, weight limits, control surface movements, engine make and model, minimum crew, fuel type, thrust limits, RPM limits, etc., and the various components eligible for installation on the product. 239. Maintenance Manual. The maintenance manual is developed by the manufacturer of the applicable product, and provides the recommended and acceptable procedures to be followed when maintaining or repairing that product. Maintenance personnel are required by regulation to follow the applicable instructions set forth by the manufacturer. The limitations section of the manual lists life limits of the product or its components that must be complied with during inspections and maintenance. Structural Repair Manual SRM. The Structural Repair Manual is developed by the manufacturer's engineering department to be used as a guideline to assist in the repair of common damage to a specific aircraft structure. It provides information for acceptable repairs of specific sections of the aircraft. Manufacturer service information. Information from the manufacturer may be in the form of information bulletins, service instructions, service bulletins, service letters, and that the manufacturer publishes to provide instructions for product improvement. Service instructions may include a recommended modification or repair that precedes the issuance of an Airworthiness Directive AD. Service letters may provide more descriptive procedures or revised sections of the maintenance manuals. They may also include instructions for the installation and repair of optional equipment, not listed in the Type Certificate Data Sheet TCDS. Airplane Assembly. Aileron Installation. The manufacturer's maintenance and illustrated parts book must be followed to ensure the correct procedures and hardware are being used for installation of the control surfaces. All of the control surfaces require specific hardware, spacers, and bearings be installed to ensure the surface does not jam or become damaged during movement. After the aileron is connected to the flight deck controls, the control system must be inspected to ensure the cable/push-pull rods are routed properly. When the balance cable is installed, check for correct attachment and operation to determine the ailerons are moving in the proper direction and opposite each other. Flap installation. Design, installation, and systems that operate flaps are as varied as the models of airplanes on which they are installed. As with any system on the specific aircraft, the manufacturer's maintenance manual and the illustrated parts book must be followed to ensure the correct procedures and parts are used. Simple flap systems are usually operated manually by cables and slasher torque tubes. Typically, many of the smaller manufactured airplane designs have flaps that are actuated by torque tubes and chained through a gearbox driven by an electric motor. Empennage installation. The empennage, consisting of the horizontal and vertical stabilizer, is not normally removed and installed unless the aircraft was damaged. Elevators, rudders, and stabilators are rigged the same as any other control surface, using the instructions provided in the manufacturer's maintenance manuals. Control operating systems. Cable systems. There are various types of cable. Material aircraft control cables are fabricated from carbon steel or stainless corrosion-resistant steel. Additionally, some manufacturers use a nylon-coated cable that is produced by extruding a flexible nylon coating over corrosion-resistant steel press cable. By adding the nylon coating to the corrosion-resistant steel cable, it increases the service life by protecting the cable strands from friction wear, keeping dirt and grit out, and dampening vibration which can work hard in the wires and long runs of cable. Cable construction. The basic component of a cable is a wire. The diameter of the wire determines the total diameter of the cable. A number of wires are preformed into a helical or spiral shape and then formed into a strand. These preformed strands are laid around the straight center strand to form a cable. Cable designations based on the number of strands and wires in each strand. The 7x19 cable is made up of 7 strands of 19 wires each. 6 of these strands are laid around the center strand. This cable is very flexible and is used in primary control systems and in other locations where operation over pulleys is frequent. The 7x7 cable consists of 7 strands of 7 wires each. 6 of these strands are laid around the center strand. This cable is of medium flexibility and is used for trim tack controls, engine controls, and indicator controls. Figure 265. 1/83/8 diameter 7x19. 7 strands, 19 wires to each strand. Diameter 1/16/3/32 diameter 7x7. 7 strands, 7 wires to each strand. Diameter. Figure 265. Cable construction and cross-section. 240. Types of control cable termination include woven splice, a hand-woven 5-tuck splice used on aircraft cable. The process is very time-consuming and produces only about 75% of the original cable strength. The splice is rarely used except on some antique aircraft, where the effort is made to keep all parts in their original configuration. Hypopress registered process, a patented process using copper sleeves, and may be used up to the full rated strength of the cable when the cable is looped around a thimble. Figure 266. This process may also be used in place of the 5-tuck splice on cables up to and including 3/8-inch diameter. Whenever this process is used for cable splicing, it is imperative that the tools, instructions, and data supplied by NicoPress registered be followed exactly, to ensure the desired cable function and strength is attained. The use of sleeves that are fabricated of material other than copper requires engineering approval for the specific application by the FAA. Swage-type terminals manufactured in accordance with Army, Navy, and military standards MS are suitable for use in civil aircraft up to, and including, maximum cable loads. Figure 267. When swaging tools are used, it is imperative that all the manufacturer's instructions, including go and no-go dimensions, be followed exactly to avoid defective and inferior swaging. Compliance with all of the instructions should result in the terminal developing the full rated strength of the cable. The following basic procedures are used when swaging terminals onto cable ends. Cut the cable to length, allowing for growth during swaging. Apply a preservative compound to the cable end before insertion into the terminal barrel. Measure the internal length of the terminal end/barrel of the fitting to determine the proper length of the cable to 312 AN 663 double shank ball end terminal, AN 664 single shank ball end terminal, AN 665 rod end terminal, AN 666 threaded cable terminal, AN 667 fork end cable terminal, AN 667 I end cable terminal. Figure 267. Swage type terminal fittings. The inserted. Transfer that measurement to the end of the cable and mark it with a piece of masking tape wrapped around the cable. This provides a positive mark to ensure the cable did not slip during the swaging process. Note: never solder the cable ends to prevent fraying, since the solder greatly increases the tendency of the cable to pull out of the terminal. Insert the cable into the terminal approximately 1 inch and bend it toward the terminal. Then, push the cable end all the way into the terminal. The bending action puts a slight kink in the cable end and provides enough friction to hold the terminal in place until the swaging operation is performed. Figure 268. Accomplish the swaging operation in accordance with the instructions furnished by the manufacturer of the swaging equipment. Figure 266. Typical NicoPress registered thimble eye splice. 241. 1. Bend cable, then push into swaging position. 2. Figure 269. Gauging terminal shank dimension after swaging. Figure 268. Insertion of cable into terminal. Inspect the terminal after swaging to determine that it is free of die marks and splits and is not out of round. Check the cable for slippage at the masking tape and for cut and broken wire strands. Using a go/no-go gauge supplied by the swaging tool manufacturer or a micrometer and swaging chart, check the terminal shank diameter for proper dimension. Figures 269 and 270. Test the cable by proof loading locally fabricated splices and newly installed swage terminal cable fittings for proper strength before installation. This is conducted by slowly applying a test load equal to 60% of the rated breaking strength of the cable listed in Figure 271. This load should be held for at least 3 minutes. Any testing of this type can be dangerous. Suitable guards should be placed over the cable during the test to prevent injury to personnel in the event of cable failure. If a proper test fixture is not available, the load test should be contracted out and performed by a properly equipped facility. Cable inspection. Aircraft cable systems are subject to a variety of environmental conditions and deterioration. Wire strand breakage is easy to recognize visually. Other kinds of deterioration, such as wear, corrosion, and distortion, are not easily seen. Special attention should be given to areas where cables pass through battery compartments, lavatories, and wheel wells. These are prime areas for corrosion. Special attention should be given to critical fatigue areas. Those areas are defined as anywhere the cable runs over, under, or around the pulley, sleeve, or through a fair lead, or any section where the cable is flexed, dubbed, or within 1 foot of a swaged-on fitting. Close inspection in these critical fatigue areas can be performed by rubbing a rag along the cable. If there are any broken strands, the rag snags on the cable. A more detailed inspection can be performed in areas that may be corroded or indicate a fatigue failure by losing or removing the cable and bending it. This technique. Before swaging, after swaging. Cable size inches. 1/16. 3/32. 1/8. 5/32. 3/16. 7/32. 1/4. 9/32. 5/16. 3/8. Wire strands. 7x7. 7x7. 7x19. 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 Outside diameter. 0.160. 0.218. 0.250. 0.297. 0.359. 0.427. 0.494. 0.563. 0.635. 0.703. Bore diameter, 0.078. 0.109. 0.141. 0.172. 0.203. 0.234. 0.265. 0.297. 0.328. 0.390. Bore length, 1.042. 1.261. 1.511. 1.761. 2.011. 2.261. 2.511. 2.761. 3.011. 3.510. Swaging length, 0.969. 1.188. 1.438. 1.688. 1.938. 2.188. 2.438. 2.688. 2.938. 3.438. Minimum braking strength pounds, 480. 920. 2000. 2800. 4200. 5600. 7000. 8000. 9800. 14400. Shank diameter star, 0.138. 0.190. 0.219. 0.250. 0.313. 0.375. 0.438. 0.500. 0.563. 0.625. Star use gauges and kit for checking diameters. Figure 270. Straight shank terminal dimensions, 242. Minimum braking strength pounds. Nominal diameter of wire rope cable. Instruction. Tolerance on diameter plus only. Allowable increase of diameter at cut end. Mil W83420. Com Bay. Mil W83420. Com B Crest. Inches. Mil C18375. Crest. Pounds. 1/32. 3/64. 1/16. 1/16. 3/32. 3/32. 1/8. 5/32. 3/16. 7/32. 1/4. 9/32. 5/16. 11/32. 3/8. 7/16. 1/2. 9/16. 5/8. 3/4. 7/8. 1. 1-1/8. 1-1/4. 1-3/8. 1-1/2. 3x7. 7x7. 7x7. 7x19. 7x7. 7x19. 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 6x19 IWRC 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 0.006 0.008 0.010 0.010 0.012 0.012 0.014 0.016 0.018 0.018 0.018 0.020 0.022 0.024 0.026 0.030 0.033 0.036 0.039 0.045 0.048 0.050 0.054 0.057 0.060 0.062 0.006 0.008 0.009 0.009 0.010 0.010 0.011 0.017 0.019 0.020 0.021 0.023 0.024 0.025 0.027 0.030 0.033 0.036 0.039 0.045 0.048 0.050 0.054 0.057 0.060 0.062 pounds 110 270 480 480 920 1000 2000 2800 4200 5000 6400 7800 9800 12500 14400 17,600, 22,800, 28,500, 35,000, 49,600, 66,500, 85,400, 106,400, 129,400, 153,600, 180,500 pounds, 110, 270, 480, 480, 920, 920, 1,760, 2,400, 3,700, 5,000, 6,400, 7,800, 9,000, 12,000, 16,300, 22,800, 28,500, 35,000, 49,600, 66,500, 85,400, 106,400, 129,400, 153,600, 180,500, 360, 700, 1,300, 2,000, 2,900, 3,800, 4,900, 6,100, 7,600, 11,000, 14,900, 19,300, 24,300, 30,100, 42,900, 58,000, 75,200. Figure 271. Flexible cable construction. Reveals internal broken strands not readily apparent from the outside. Figure 272. Cable system installation. Cable guides. Pulleys are used to guide cables, and also to change the direction of cable movement. Pulley bearings are sealed, and need no lubrication other than the lubrication done at the factory. Brackets fastened to the structure of the aircraft support the pulleys. Cables passing over pulleys are kept in place by guards. The guards are close-fitting to prevent jamming, or to prevent the cables from slipping off when they slacken due to temperature variations. Pulleys should be examined to ensure proper lubrication, smooth rotation and freedom from abnormal cable wear patterns which can provide an indication of other problems in the cable system. Figure 273. Figure 272. Cable inspection technique. 243. Excessive cable tension pulley wear from misalignment. Pulley too large for cable misalignment. Frozen bearing normal condition. Figure 273. Pulley wear patterns. Fairleads may be made from a non-metallic material, such as phenolic, or a metallic material, such as soft aluminum. The fairlead completely encircles the cable, where it passes through holes in bulkheads or other metal parts. Fairleads are used to guide cables in a straight line through or between structural members of the aircraft. Fairleads should never deflect the alignment of a cable more than 3 degrees from a straight line. Pressure seals are installed where cables or rods move through pressure bulkheads. The seal grips tightly enough to prevent excess air pressure loss, but not enough to hinder movement of the cable. Pressure seals should be inspected at regular intervals to determine that the retaining rings are in place. If a retaining ring comes off, it may slide along the cable and cause jamming of a pulley. Figure 274. Travel adjustment. Control surfaces should move a certain distance in either direction from the neutral position. These movements must be synchronized with the movement of the flight deck controls. The flight control system must be adjusted rigged to obtain these requirements. The tools for measuring surface travel primarily include protractors, rigging fixtures, contour templates, and rulers. These tools are used when rigging flight control systems to assure that the desired travel has been obtained. Generally speaking, the rigging consists of the following. 1. Positioning the flight control system in neutral, and temporarily locking it there with rig pins or blocks. 2. Adjusting system cable tension and maintaining rudder, elevator, and ailerons in the neutral position. And 3. Adjusting the control stops to the aircraft manufacturer's specifications. Fairlead, rupstrip, split fairlead, solid fairlead, retaining rings, control cable, guard pin, bulkhead groove, pressurized unpressurized, bracket, air seal bulkhead, pulley. Figure 274. Cable guides. 244. Cable tension. For the aircraft to operate as it was designed, the cable tension for the flight controls must be correct. To determine the amount of tension on the cable, a tensiometer is used. When properly maintained, a tensiometer is 98% accurate. Cable tension is determined by measuring the amount of force needed to make an offset in the cable between two hardened steel blocks called anvils. A riser or plunger is pressed against the cable to form the offset. Several manufacturers make a variety of tensiometers, each type designed for different kinds of cable sizes, and cable tensions. Figure 275. Rigging fixtures. Rigging fixtures and templates are special tools gauges designed by the manufacturer to measure control surface travel. Markings on the fixture or template indicate desired control surface travel. Tension regulators. Cable tension regulators are used in some flight control systems, because there is considerable difference in temperature expansion of the aluminum aircraft structure and the steel control cables. Some large aircraft incorporate tension regulators in the control cable systems, to maintain a given cable tension automatically. The unit consists of a compression spring and a locking mechanism, that allows the spring to make correction in the system, only when the cable system is in neutral. Turnbuckles. A turnbuckle assembly is a mechanical screw device consisting of two threaded terminals and a threaded barrel. Figure 276 turnbuckles are fitted in the cable assembly for the purpose of making minor adjustments in cable length, and for adjusting cable tension. One of the terminals has right-hand threads, and the other has left-hand threads. The barrel has matching right and left-hand internal threads. The end of the barrel with the left-hand threads can usually be identified by a groove, or knurl around that end of the barrel. When installing a turnbuckle in a control system, it is pointer lock, riser anvil, anvil, 0, 20, 40, 60, 120, 180, trigger, figure 275, tensiometer. Necessary to screw both of the terminals an equal number of turns into the barrel. It is also essential that all turnbuckle terminals be screwed into the barrel until not more than 3 threads are exposed on either side of the turnbuckle barrel. After a turnbuckle is properly adjusted, it must be safetied. There are a number of methods to safety a turnbuckle, and or other types of swaged cable lengths that are satisfactory. A double-wrap safety wire method is preferred. Some turnbuckles are manufactured and designed to accommodate special locking devices. A typical unit is shown in figure 277. Cable connectors. In addition to turnbuckles, cable connectors are used in some systems. These connectors enable a cable length to be quickly connected or disconnected from a system. Figure 278 illustrates one type of cable connector in use. Spring back. With a control cable properly rigged, the flight control should hit its stops at both extremes prior to the flight deck control. Length threads flush with ends of barrel. Swaged terminal barrel pin I. Figure 276. Typical turnbuckle assembly. 245. Turnbuckle body locking clip. Figure 277. Clip type locking device and assembling in turnbuckle. Spring connector. Figure 278. Spring type connector. The spring back is the small extra push that is needed for the flight deck control to hit its mechanical stop. Push rods control rods. Push rods are used as links in the flight control system, to give push-pull motion. They may be adjusted at one or both ends. Figure 279 shows the parts of a push rod. Notice that it consists of a tube with threaded rod ends. An adjustable anti-friction rod end, or rod end clevis, attaches at each end of the tube. The rod end, or clevis, permits attachment of the tube to flight control system parts. The check nut, when tightened, prevents the rod end or clevis from loosening. They may have adjustments at one or both ends. The rods should be perfectly straight, unless designed to be otherwise. When installed as part of a control system, the assembly should be checked for correct alignment and free movement. It is possible for control rods fitted with bearings to become disconnected, because of failure of the peening that retains the ball races in the rod end. This can be avoided by installing the control rods, so that the flange of the rod end is interposed between the ball race and the anchored end of the attaching pin or bolt as shown in figure 280. Check nut threaded rod end. Tube. Adjustable anti-friction rod end rivets. Figure 279. Push rod. 246. Adjustable rod end clevis. Anchored end. Quadrant. Flange. Flange ends. Peening. Torque tube. Figure 280. Attached rod end. Another alternative is to place a washer, having a larger diameter than the hole in the flange, under the retaining nut on the end of the attaching pin or bolt. This retains the rod on the bolt in the event of a bearing failure. Torque tubes. Where an angular or twisting motion is needed in a control system, a torque tube is installed. Figure 281 shows how a torque tube is used to transmit motion in opposite directions. Cable drums. Cable drums are used primarily in trim tab systems. As the trim tab control wheel is moved clockwise or counterclockwise, horn. Push-pull rod. Figure 281. Torque tube. Cable drum winds or unwinds to actuate the trim tab cables. Figure 282. Bearing. Shaft drum. Control wheel. Figure 282. Trim tab cable drum. 247. Rigging checks. All aircraft assembly and rigging must be performed in accordance with the requirements prescribed by the specific aircraft and /aircraft component manufacturer. Correctly following the procedures provides for proper operation of the components in regard to their mechanical and aerodynamic function, and ensures the structural integrity of the aircraft. Rigging procedures are detailed in the applicable manufacturer's maintenance or service manuals and applicable structural repair manuals. Additionally, aircraft specification or TCDS also provide information regarding control surface movement and weight and balance limits. The purpose of this section is to explain the methods of checking the relative alignment and adjustment of an aircraft's main structural components. It is not intended to imply that the procedures are exactly as they may be in a particular aircraft. When rigging an aircraft, always follow the procedures and methods specified by the aircraft manufacturer. Structural alignment. The position or angle of the main structural components is related to a longitudinal datum line parallel to the aircraft center line, and a lateral datum line parallel to a line joining the wing tips. Before checking the position or angle of the main components, the aircraft must be jacked and leveled. Small aircraft usually have fixed pegs or blocks attached to the fuselage parallel to, or coincident with the datum lines. A spirit level and a straight edge are rested across the pegs, or blocks to check the level of the aircraft. This method of checking aircraft level also applies to many of the larger types of aircraft. However, the grid method is sometimes used on large aircraft. The grid plate is a permanent fixture installed on the aircraft floor or supporting structure. Figure 283. When the aircraft is to be leveled, a plumb bob is suspended from a predetermined position in the ceiling of the aircraft over the grid plate. The adjustments to the jacks necessary to level the aircraft are indicated on the grid scale. The aircraft is level when the plumb bob is suspended over the center point of the grid. Certain precautions must be observed in all instances when jacking an aircraft. Normally, rigging and alignment checks should be performed in an enclosed hangar. If this cannot be accomplished, the aircraft should be positioned with the nose into the wind. The weight and loading of the aircraft should be exactly as described in the manufacturer's manual. In all cases, the aircraft should not be jacked until it is determined that the maximum jacking weight, if applicable specified by the manufacturer, is not exceeded. With a few exceptions, the dihedral and incidence angles of conventional modern aircraft cannot be adjusted. Some manufacturers permit adjusting the wing angle of incidence to correct for a wing-heavy condition. The dihedral and incidence angles should be checked after hard landings or after experiencing abnormal flight loads to ensure that the components are not distorted and that the angles are within the specified limits. There are several methods for checking structural alignment and rigging angles. Special rigging boards that incorporate, or on which can be placed, a special instrument spirit level or inclinometer for determining the angle are used on some aircraft. On a number of aircraft, the alignment is checked using a transit, and plumb bobs are a theodolite and sighting rods. The particular equipment to use is usually specified in the manufacturer's maintenance manual. When checking alignment, a suitable sequence should be developed and followed to be certain that the checks are made at all the positions specified. The alignment checks specified usually include wing dihedral angle, wing incidence angle, verticality of the fin, engine alignment, a symmetry check, horizontal stabilizer incidence, horizontal stabilizer dihedral, checking dihedral. The dihedral angle should be checked in the specified positions using the special boards provided by the aircraft manufacturer. If no such boards are available, a straight edge and an inclinometer can be used. The methods for checking dihedral are shown in Figure 284. It is important that the dihedral be checked at the positions specified by the manufacturer. Certain portions of the wings or horizontal stabilizer may sometimes be horizontal or, on rare occasions, antihedral angles may be present. Checking incidence. Incidence is usually checked in at least two specified positions on the surface of the wing to ensure that the wing is free from twist. A variety of incidence boards are used to check the incidence angle. Some have stops at the forward. 248. Plumb bob attachment. Right main wheel wall aft bulkhead. Aft. INDD. Nose up. 3. Plumb bob stowage clip. 2. 1. Hitch deck. 0. Plumb bob. Nose down. 1, 2, 3. Right wing down. Roll deck. Grid plate. 1, 2, 3. Left wing down. Figure 283. Grid plate installed. Special dihedral board with spirit level incorporated. Straight edge and adjustable level. Figure 284. Checking dihedral. 249. Bubble level. Stop. Straight edge and adjustable level. Incidence board. Board line. Figure 285. A typical incidence board. Edge, which must be placed in contact with the leading edge of the wing. Others are equipped with location pegs which fit into some specified part of the structure. The purpose in either case is to ensure that the board is fitted in exactly the position intended. In most instances, the boards are kept clear of the wing contour by short extensions attached to the board. A typical incidence board is shown in Figure 285. When used, the board is placed at the specified locations on the surface being checked. If the incidence angle is correct, the inclinometer on top of the board reads 0, or within a specified tolerance of 0. Modifications to the areas where incidence boards are located can affect the reading. For example, if leading edge de-icer boots have been installed, the position of a board having a leading edge stop is affected. Checking fin verticality. After the rigging of the horizontal stabilizer has been checked, the verticality of the vertical stabilizer relative to the lateral datum can be checked. The measurements are taken from a given point on either side of the top of the fin to a given point on the left and right horizontal stabilizers. Figure 286. The measurements should be similar within prescribed limits. When it is necessary to check the alignment of the rudder hinges, remove the rudder and pass a plumb bob line through the rudder hinge attachment holes. The line should pass centrally through all the holes. It should be noted that some aircraft have the leading edge of the vertical fin offset to the longitudinal center line to counteract engine torque. Checking engine alignment. Engines are usually mounted with the thrust line parallel to the horizontal longitudinal plane of symmetry. However, this is not always true when the engines are mounted on the wings. Checking to ensure that the position of the engines, including any degree of offset, is correct, depends largely on the type of mounting. Generally, the check entails a measurement from the center line of the mounting to the longitudinal center line of the fuselage at the point specified in the applicable manual. Figure 287. String or tape measure lateral datum. Figure 286. Checking fin verticality. 250. Figure 287. Typical measurements used to check aircraft symmetry. Symmetry check. The principle of a typical symmetry check is illustrated in Figure 287. The precise figures, tolerances, and checkpoints for a particular aircraft are found in the applicable service or maintenance manual. On small aircraft, the measurements between points are usually taken using a steel tape. When measuring long distances, it is suggested that a spring scale be used with the tape to obtain equal tension. A 5-pound pull is usually sufficient. On large aircraft, the positions at which the dimensions are to be taken are usually chalked on the floor. This is done by suspending a plumb bob from the checkpoints and marking the floor immediately under the point of each plumb bob. The measurements are then taken between the centers of each marking. Cable tension. When it has been determined that the aircraft is symmetrical and structural alignment is within specifications, the cable tension and control surface travel can be checked. To determine the amount of tension on the cable, a tensiometer is used. When properly maintained, a tensiometer is 98% accurate. Cable tension is determined by measuring the amount of force needed to make an offset in the cable between two hardened steel blocks called anvils. A riser or plunger is pressed against the cable to form the offset. Several manufacturers make a variety of tensiometers, each type designed for different kinds of cable, cable sizes, and cable tensions. One type of tensiometer is illustrated in Figure 288. Pointer lock. Anvil. Riser anvil. 0, 20, 40, 60, 120, 180. Trigger. Example. No. 1 riser no. 2 no. 3. Diameter 1/16 3/32 1/8. 12. 19. 25. 31. 36. 41. 46. 51. 16. 23. 30. 36. 42. 48. 54. 60. 21. 29. 36. 43. 50. 57. 63. 69. Tension LP. 30. 40. 50. 60. 70. 80. 90. 100. 110. 120. 5/32 3/16 7/32 1/4. 12. 17. 22. 26. 30. 34. 38. 42. 46. 50. 20. 26. 32. 37. 42. 47. 52. 56. 60. 64. Figure 288. Cable tensiometer and sample conversion chart. 251. Following the manufacturer's instructions, lower the trigger. Then, place the cable to be tested under the two anvils, and close the trigger, move it up. Movement of the trigger pushes up the riser, which pushes the cable at right angles to the two clamping points under the anvils. The force that is required to do this is indicated by the dial pointer. As the sample chart beneath the illustration shows, different numbered risers are used with different size cables. Each riser has an identifying number and is easily inserted into the tensiometer. Included with each tensiometer is a conversion chart, which is used to convert the dial reading to pounds. The dial reading is converted to pounds of tension as follows. Using a No.2 riser to measure the tension of a 5/32 diameter cable, a reading of 30 is obtained. The actual tension C chart of the cable is 70 lbs. Referring to the chart, also notice that a No.1 riser is used with 1/16, 3/32, and 1/8 cable. Since the tensiometer is not designed for use in measuring 7/32 or 1/4 cable, no values are shown in the No.3 riser column of the chart. When actually taking a reading of cable tension in an aircraft, it may be difficult to see the dial. Therefore, a pointer lock is built in on the tensiometer. Push it in to lock the pointer, then remove the tensiometer from the cable and observe the reading. After observing the reading, pull the lock out and the pointer returns to 0. Another variable that must be taken into account when adjusting cable tension is the ambient temperature of cable on the aircraft. To compensate for temperature variations, cable rigging charts are used when establishing cable tensions in flight control, landing gear, and other cable-operated systems. Figure 289. To use the chart, determine the size of the cable that is to be adjusted, and the ambient air temperature. For example, assume that the cable size is 1/8 diameter, which is a 719 cable, and the ambient air temperature is 85 degrees F. Follow the 85 degrees F line upward to where it intersects the curve for 1/8 cable. Extend the horizontal line from the point of intersection to the right edge of the chart. The value at this point indicates the tension rigging load in pounds to establish on the cable. The tension for this example is 70 pounds. Design limit rig load. Cable size 1/47x19, 3/167x19. Rigging load LB 5/327x19, 1/87x19, 3/327x7, 1/167x7, 340, 320, 300, 280, 260, 240, 220, 200, 180, 160, 140, 120, 100, 80, 60, 40, 20, 0, 70, 60, 50, 40, 30, 20, 10, 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160. Temperature degrees F. Figure 289. Typical cable rigging chart. 252. Control surface travel. In order for a control system to function properly, it must be correctly adjusted. Correctly rigged control surfaces move through a prescribed arc surface throw and are synchronized with the movement of the flight deck controls. Rigging any control system requires that the aircraft manufacturer's instructions be followed as outlined in their maintenance manual. Therefore, the explanations in this chapter are limited to the 3 general steps listed below. 1. Lock the flight deck control, bell cranks, and the control surfaces in the neutral position. 2. Adjust the cable tension, maintaining the rudder, elevators, or ailerons in the neutral position. 3. Adjust the control stops to limit the control surface travel to the dimensions given for the aircraft being rigged. The range of movement of the controls and control surfaces should be checked in both directions from neutral. There are various tools used for measuring surface travel, including protractors, rigging fixtures, contour templates, and rulers. These tools are used when rigging flight control systems to ensure that the aircraft is properly rigged and the manufacturer's specifications have been complied with. Rigging fixtures and contour templates are special tools gauges designed by the manufacturer to measure control surface travel. Markings on the fixture or template indicate desired control surface travel. In many instances, the aircraft manufacturer gives the travel of a particular control surface in degrees and inches. If the travel in inches is provided, a ruler can be used to measure surface travel in inches. Protractors are tools for measuring angles in degrees. Various types of protractors are used to determine the travel of flight control surfaces. One protractor that can be used to measure aileron, elevator, or wing flap travel is the universal propeller protractor shown in figure 290. This protractor is made up of a frame, disc, ring, and 2 spirit levels. The disc and ring turn independently of each other and of the frame. The center spirit level is used to position the frame vertically when measuring propeller blade angle. The center spirit level is used to position the disc when measuring control surface travel. A disc to ring lock is provided to secure the disc and ring together when the 0 on the ring vernier scale and the 0 on the disc degree scale align. The ring to frame lock prevents the ring from moving when the disc is moved. Note that they start at ring vernier scale, center spirit level disc adjuster ring, disc degree scale, disc, ring adjuster, 10, 0, 10, 30 20 10, 0, 10 20 30, corner spirit level ring to frame lock on frame folded in. Disc to ring lock on ring engages only when zeros on scales are aligned. Figure 290. Universal propeller protractor. The same point and advance in opposite directions. A double 10-part vernier is marked on the ring. The rigging of the trim tab systems is performed in a similar manner. The trim tab control is set to the neutral no trim position, and the surface tab is usually adjusted to streamline with the control surface. However, on some aircraft, the specifications may require that the trim tabs be offset a degree or 2 from streamline when in the neutral position. After the tab and tab control are in the neutral position, adjust the control cable tension. Pins, usually called rig pins, are sometimes used to simplify the setting of pulleys, levers, bell cranks, and their neutral positions. A rig pin is a small metallic pin or clip. When rig pins are not provided, the neutral positions can be established by means of alignment marks, by special templates, or by taking linear measurements. If the final alignment and adjustment of a system are correct, it should be possible to withdraw the rigging pins easily. Any undue tightness of the pins in the rigging balls indicates incorrect tensioning or misalignment of the system. 253. After a system has been adjusted, the full and synchronized movement of the controls should be checked. When checking the range of movement of the control surface, the controls must be operated from the flight deck and not by moving the control surfaces. During the checking of control surface travel, ensure that chains, cables, have not reached the limit of their travel when the controls are against their respective stops. Adjustable and non-adjustable stops, whichever the case requires, are used to limit the throw range or travel movement of the ailerons, elevator, and rudder. Usually there are 2 sets of stops for each of the 3 main control surfaces. One set is located at the control surface, either in the snubber cylinders, or as structural stops, the other, at the flight deck control. Either of these may serve as the actual limit stop. However, those situated at the control surface usually perform this function. The other stops do not normally contact each other, but are adjusted to a definite clearance when the control surface is at the full extent of its travel. These work as override stops to prevent stretching of cables and damage to the control system during violent maneuvers. When rigging control systems, refer to the applicable maintenance manual for the sequence of steps for adjusting these stops to limit the control surface travel. Where dual controls are installed, they must be synchronized and function satisfactorily when operated from both positions. Trim tabs and other tabs should be checked in a manner similar to the main control surfaces. The tab position indicator must be checked to see that it functions correctly. If jack screws are used to actuate the trim tab, check to see that they are not extended beyond the specified limits when the tab is in its extreme positions. After determining that the control system functions properly and is correctly rigged, it should be thoroughly inspected to determine that the system is correctly assembled and operates freely over the specified range of movement. Checking and safetying the system. Whenever rigging is performed on any aircraft, it is good practice to have a second set of eyes inspect the control system to make certain that all turnbuckles, rod ends, and attaching nuts and bolts are correctly safetied. As a general rule, all fasteners on an aircraft are safetied in some manner. Safetying is defined as securing by various means any nut, bolt, turnbuckle, on the aircraft so that vibration does not cause it to loosen during operation. Small screw and closely spaced closed geometrical pattern single twist method. Single fastener application double twist method. Screw heads double twist method. External snap ring single wire method. Hassle nuts. Bolt heads. Figure 291. Double wrap and single safety wire methods for nuts, bolts, and snap rings. 254. Most aircraft manufacturers have a standard practices section in their maintenance manuals. These are the methods that should be used when working on a particular system of a specific aircraft. However, most standard aircraft hardware has a standard method of being safetied. The following information provides some of the most common methods used in aircraft safetying. The most commonly used safety wire method is the double twist, utilizing stainless steel or mono wire in the .032 to .040 inch diameter range. This method is used on studs, cable turnbuckles, flight controls, and engine accessory attaching bolts. A single wire method is used on smaller screws, bolts, and slasher nuts when they are located in a closely spaced or closed geometrical pattern. The single wire method is also used on electrical components and in places that are difficult to reach. Figure 291. Safety of flight emergency equipment, such as portable fire extinguishers, oxygen regulators, emergency valves, firewall shutoffs, and seals on first aid kits, are safetied using a single copper wire .020 inch diameter or aluminum wire .031 inch diameter. The wire on this emergency equipment is installed only to indicate the component is sealed or has not been actuated. It must be possible to break the wire seal by hand, without the use of any tools. The use of safety wire pliers, or wire twisters, makes the job of safetying much easier on the mechanic's hands, and produces a better finished product. Figure 292. Outer sleeve. The lock jaws. Plier handles will spin when knob is pulled. Pull knob to twist wire. The wire should have 6 to 8 twists per inch of wire, and be pulled taut while being installed. Where practicable, install the safety wire around the head of the fastener and twist it in such a manner that the loop of the wire is pulled close to the contour of the unit being safety wired, and in the direction that would have the tendency to tighten the fastener. Figure 293. Cotter pins are used to secure such items as bolts, screws, pins, and shafts. They are used at any location where a turning or actuating movement takes place. The diameter of the cotter pin selected for any application should be the largest size that will fit consistent with the diameter of the cotter pin ball and slash, or the slots in the castellated nut. Cotter pins, like safety wire, should never be reused on aircraft. Figure 294. Self-locking nuts are used in applications where they are not removed often. There are two types of self-locking nuts currently in use. One is all metal and the other as an insert, usually of fiber or nylon. It is extremely important that the manufacturer's illustrated parts book IPB be consulted for the correct type and grade of lock nut for various locations on the aircraft. The finisher plating color of the nut identifies the type of application and environment in which it can be used. For example, a cadmium-plated nut is gold in color and provides exceptionally good protection against corrosion, but should not be used in applications where the temperature may exceed 450 degrees F. Repeated removal and installation causes the self-locking nut to lose its locking feature. They should be replaced when they are no longer capable of maintaining the minimum prevailing torque. Figure 295. Lock washers may be used with bolts and machine screws whenever a self-locking nut or castellated nut is not applicable. They may be of the split washer spring type, or a multi-serrated internal or external star washer. Al nuts may be a second nut tightened against the first and used to force the primary nut thread against the bolt or screw thread. They may also be of the type that are made of stamped spring steel and are to be used only once and replaced with new ones when removed. Biplane assembly and rigging. Biplanes were some of the very first aircraft designs. The first powered heavier-than-air aircraft, the Wright brothers' Wright Flyer, successfully flown on December 17, 1903, was a biplane. Figure 292. Use of safety wire pliers or wire twisters. 255. Example 1, Example 2, Example 3, Example 4, Example 5, Example 6, Example 7, Example 8, Example 9, Example 10. Correct application of single wire to closely spaced multiple group. Fittings incorporating wire lugs shall be wired as shown in 7 and 8. Where no lock wire lug is provided, wire should be applied as shown in 9 and 10 with caution, being exerted to ensure that wire is wrapped tightly around the fitting. Example 6. Example 10. Coupling nuts attached to straight connectors shall be wired as shown, when X is an integral part of the connector. Examples apply to all types of bolts, Philister head screws, square head plugs, and other similar parts which are wired, so that the loosening tendency of either part is counteracted by tightening of the other part. The direction of twist from the second to the third unit is counterclockwise in examples, to keep the loop in position against the head of the bolt. The wire entering the hole in the third unit is the lower wire, and by making a counterclockwise twist after it leaves the hole, the loop is secured in place around the head of that bolt. Example shows methods for wiring various standard items. Note: wire may be wrapped over the unit, rather than around it when wiring castellated nuts, or on other items, when there is clearance problem. Coupling nuts on the T shall be wired, as shown above, so that tension is always in the tightening direction. Figure 293. Examples of various fasteners and methods of safetying. 256. Figure 294. Securing hardware with cotter pins. Find thread series. Thread size. 7/16-20. 1/2-20. 9/16-18. 5/8-18. 3/4-16. 7/8-14. 1-14. 11/8-12. 11/4-12. Minimum prevailing torque. 8 inch-pounds, 10 inch-pounds, 13 inch-pounds, 18 inch-pounds, 27 inch-pounds, 40 inch-pounds, 55 inch-pounds, 73 inch-pounds, 94 inch-pounds. Horse thread series. Thread size. 7/16-14. 1/2-13. 9/16-12. 5/8-11. 3/4-10. 7/8-9. 1-8. 11/8-8. 11/4-8. Minimum prevailing torque. 8 inch-pounds, 10 inch-pounds, 14 inch-pounds, 20 inch-pounds, 27 inch-pounds, 40 inch-pounds, 51 inch-pounds, 68 inch-pounds, 68 inch-pounds. Figure 295. Minimum prevailing torque values for reused self-locking nuts. The first biplanes were designed with very thin wing sections and, consequently, the wing structure needed to be strengthened by external bracing wires. The biplane configuration allowed the two wings to be braced against one another, increasing the structural strength. When the assembly and rigging of a biplane is accomplished in accordance with the approved instructions, a stable airworthy aircraft is the result. Whether assembling an early model vintage aircraft that may have been disassembled for repair and restoration, or constructing and assembling a new aircraft, the following are some basic alignment procedures to follow. To start, the fuselage must be level, fore and aft and laterally. The aircraft usually has specific leveling points designated by the manufacturer or indicated on the plans. The fuselage should be blocked up off the landing gear, so it is stable. A center line should be drawn on the floor the length of the fuselage, and another line perpendicular to it at the firewall, for use as an additional alignment reference. With the horizontal and vertical tail surfaces installed, the incident angle for the horizontal stabilizer should be set. The tail brace wires should be connected, and tightened until the slack is removed. Alignment measurements should be checked as shown in Figure 296. Select easy to identify points from which to cross-measure. Note: make cross-measurements with a 50 steel tape. Ideally, distances on both sides should match. A 1 to 2/B1 B2, egg. 90 degrees. Firewall center line. B1 C1 C2 B2 D1 D2. Reference point. Top view. Vertical tail post reference. A 2-1. 90 degrees. Rear view. Figure 296. Checking aircraft symmetry. 257. Install the elevator and rudder, and clamp them in a neutral position. Verify the neutral position of the control stick and rudder pedals in the flight deck, and secure them, in order to simplify the connecting and final tensioning of the control cables. If the biplane has a center section for the upper wing, it must be aligned as accurately as possible, because even the smallest error is compounded at the wing tip. Applicable cables and turnbuckles should be connected, and the tension set as specified. Figure 297. The stagger measurement can be checked as shown in Figure 298. The lower wing sections should be individually attached to the fuselage and locked up for support, while the landing wires are connected and adjusted to obtain the dihedral called for in the specifications or plans. Figure 299. Spar. Plumb bob stagger lower wing hinge fittings. Plumb line. Ruler. Plumb bob. Level aircraft. Stagger measured in inches. Fuselage center line. 90 degrees. 90 degrees. Center section. Top view. Both tie rods Z same length. 90 degrees. ZZ. Distance X same both sides. XX. Ruler. 98765432112345678 Distance Y same both sides straight edge clamp to firewall. Level. Front view. Figure 298. Measuring stagger. Plumb bobs or weights. X1 X2. To increase dihedral shorten landing wires. Wood blocks 2x4. Upper wing with 0 degrees dihedral string must touch blocks. Plumb bobs or weights. X1 X2. Landing wires. 4 degrees 4 degrees. Use straight edge and bevel protractor. Can also use dihedral board with a level. Measure upper wing dihedral. Dihedral board. Steered level. Lower wing dihedral in inches. Measuring dihedral in inches. Measuring dihedral angles. Plumb bob. Depicted angle 4 degrees. 4 degrees 57. Note: a 1 rise in 57 equals 1 degree of dihedral. Figure 297. Center section alignment. 258. Figure 299. Measuring dihedral. Next, connect the outer end struts to the left and right sections of the lower wing. Now, the upper wing can be attached, and the flying wires installed. The slave struts can be installed, and the ailerons connected using the same alignment and adjustment procedures used for the elevator and rudder. The incidence angle can be checked, as shown in Figure 2100. Once this point is reached, it is a matter of measuring, checking angles, and adjusting the various components to obtain the overall aircraft symmetry and desired alignment, as shown in Figure 296. Also, remember that care should be used when tightening the wing wires, because extra stress can be inadvertently induced into the wings. Always loosen one wire, before tightening the opposite wire. Flying and landing wires are typically set at about 600 pounds and tail brace wires at about 300 pounds of tension. When convinced the aircraft is properly rigged, move away from it, and take a good look at the finished product. Are the wings symmetrical? Does the dihedral look even? Is the tail section square with the fuselage? Are the wing attaching hardware, flying wires, and control cables safetied? And the final task, before the first flight, is to complete the maintenance record entries. 1. Chord line make bottom parallel with chord line make rib template to measure incidence of acrobatic type wings. Aircraft must be level when checking incidence. Plywood. 2. Wing incidence angle. Bevel protractor. Use straight edge for flat bottom airfoils Clark Y series, EC. Measurement for angle of incidence. Steered level. Level. Aircraft jog wheels. Straight edge. Figure 2100. Checking incidence. As with any aircraft maintenance or repair, the instructions and specifications from the manufacturer, or the procedures and recommendations found in the construction plans, should be the primary method to perform the assembly and rigging of the aircraft. Aircraft inspection. Purpose of inspection programs. The purpose of an aircraft inspection program is to ensure that the aircraft is airworthy. The term airworthy is not defined in the 14 CFR. However, case law relating to the term and regulations for the issuance of a standard airworthiness certificate reveal 2 conditions that must be met for the aircraft to be considered airworthy. 1. The aircraft must conform to its type design or properly altered condition. Conformity to type design is considered attained when the aircraft configuration and the components installed are consistent with the drawings, specifications, and other data that are part of the TC, which includes any supplemental type certificate STC and field-approved alterations incorporated into the aircraft. 2. The aircraft must be in a condition for safe operation. This refers to the condition of the aircraft relative to wear and deterioration, e.g., skin corrosion, window delamination/grazing, fluid leaks, and tire wear beyond specified limits. When flight hours and calendar time are accumulated into the life of an aircraft, some components wear out and others deteriorate. Inspections are developed to find these items, and repair or replace them, before they affect the airworthiness of the aircraft. Perform an airframe conformity and airworthiness inspection. To establish conformity of an aircraft product, start with a TCDS. This document is a formal description of the aircraft, the engine, or the propeller. It is issued by the Federal Aviation Administration (FAA) when they find that the product meets the applicable requirements for certification under 14 CFR. The TCDS lists the limitations and information required for type certification of aircraft. It includes the certification basis and eligible serial numbers for the product. It lists airspeed limits, weight limits, control surface movements, engine make and models, minimum crew, fuel type, EC, the horsepower and RPM limits, thrust limitations, size and weight for engines, and blade diameter, pitch, EC, for propellers. 259. Additionally, it provides all the various components by make and model, eligible for installation on the applicable product. A manufacturer's maintenance information may be in the form of service instructions, service bulletins, or service letters that the manufacturer publishes to provide instructions for product improvement, or to revise and update maintenance manuals. Service bulletins are not regulatory unless 1. All or a portion of a service bulletin is incorporated as part of an airworthiness directive. 2. The service bulletins are part of the FAA-approved airworthiness limitations section of the manufacturer's manual, or part of the type certificate. 3. The service bulletins are incorporated directly, or by reference into an FAA-approved inspection program, such as an approved aircraft inspection program or continuous aircraft maintenance program CAMP. 4. The service bulletins are listed as an additional maintenance requirement in the certificate holder's operations specifications (OPSPECs). Airworthiness directives ADs are published by the FAA as amendments to 14 CFR Part 39, Section 39.13. They apply to the following products: aircraft, aircraft engines, propellers, and appliances. The FAA issues airworthiness directives when an unsafe condition exists in a product, and the condition is likely to exist or develop in other products of the same type design. To perform the airframe conformity and verify the airworthiness of the aircraft, records must be checked and the aircraft inspected. The data plate on the airframe is inspected to verify its make, model, serial number, type certificate, or production certificate. Check the registration and airworthiness certificate to verify they are correct and reflect the N number on the aircraft. Inspect aircraft records. Check current inspection status of aircraft by verifying the date of the last inspection and aircraft total time in service, the type of inspection, and if it includes manufacturer's bulletins, the signature, certificate number, and the type of certificate of the person who returned the aircraft to service. Identify if any major alterations or major repairs have been performed, and recorded on an FAA Form 337, Major Repair and Alteration. Review any flight manual supplements FMS included in the pilot's operating handbook and determine if there are any airworthiness limitations or required placards associated with the installation that must be inspected. Check for a current weight and balance report and the current equipment list, current status of airworthiness directives for airframe, engine, propeller, and appliances. Also, check the limitations section of the manufacturer's manual to verify the status of any life-limited components. Obtain the latest revision of the airframe TCDS and use it as a verification document to inspect and ensure the correct engines, propellers, and components are installed on the airframe. Required inspections. Pre-flight. Pre-flight for the aircraft is described in the PO for that specific aircraft and should be followed with the same attention given to the checklists for takeoff, in-flight, and landing checklists. Periodic maintenance inspections. Annual inspection. With few exceptions, no person may operate an aircraft unless, within the preceding 12 calendar months, it has had an annual inspection in accordance with 14 CFR Part 43 and was approved for return to service by a person authorized under Section 43.7. A certificated mechanic with an airframe and power plant A and P rating must hold an inspection authorization IA to perform an annual inspection. A checklist must be used, and include as a minimum, the scope and detail of items as applicable to the particular aircraft in 14 CFR Part 43, Appendix D. 100-hour inspection. This inspection is required when an aircraft is operated under 14 CFR Part 91 and used for hire, such as flight training. It is required to be performed every 100 hours of service in addition to the annual inspection. The inspection may be performed by a certificated mechanic with an A&P rating. A checklist must be used, and as a minimum, the inspection must include the scope and detail of items as applicable to the particular aircraft in 14 CFR Part 43, Appendix D. Progressive inspection. This inspection program can be performed under 14 CFR Part 91, Section 91.409D, as an alternative to an annual inspection. However, the program requires that a written 260 request be submitted by the registered owner or operator of an aircraft desiring to use a progressive inspection to the local FAA Flight Standards District Office FS2. It shall provide 1. The name of a certificated mechanic holding an inspection authorization, a certificated airframe repair station, or the manufacturer of the aircraft to supervise or conduct the inspection. 2. A current inspection procedures manual available and readily understandable to the pilot and maintenance personnel containing in detail an explanation of the progressive inspection, including the continuity of inspection responsibility, the making of reports, and the keeping of records and technical reference material. An inspection schedule, specifying the intervals in hours or days when routine and detailed inspections will be performed, and including instructions for exceeding an inspection interval by not more than 10 hours while en route, and for changing an inspection interval because of service experience. Sample routine and detailed inspection forms and instructions for their use. Sample reports and records and instructions for their use. 3. Enough housing and equipment for necessary disassembly and proper inspection of the aircraft. 4. Appropriate current technical information for the aircraft. The frequency and detail of the progressive inspection program shall provide for the complete inspection of the aircraft within each 12 calendar months, and be consistent with the manufacturer's recommendations and kind of operation in which the aircraft is engaged. The progressive inspection schedule must ensure that the aircraft will be airworthy at all times. A certificated A&P mechanic may perform a progressive inspection, as long as he or she is being supervised by a mechanic holding an inspection authorization. If the progressive inspection is discontinued, the owner or operator must immediately notify the local FAA FS2 in writing. After discontinuance, the first annual inspection will be due within 12 calendar months of the last complete inspection of the aircraft under the progressive inspection. Large airplanes over 12,500 lb. Inspection requirements of 14 CFR Part 91, Section 91.409, to include paragraph C and F. Paragraph E applies to large airplanes to which 14 CFR Part 125 is not applicable, turbojet multi-engine airplanes, turbo-propeller-powered multi-engine airplanes, and turbine-powered rotorcraft. Paragraph F lists the inspection programs that can be selected under paragraph E. The additional inspection requirements for these aircraft are placed on the operator, because the larger aircraft typically are more complex, and require a more detailed inspection program than is provided for in 14 CFR Part 43, Appendix D. An inspection program must be selected from one of the following 4 options by the owner or operator of the aircraft. 1. A continuous airworthiness inspection program that is part of a continuous airworthiness maintenance program currently in use by a person holding an air carrier operating certificate or an operating certificate issued under 14 CFR Part 121 or 135. 2. An approved aircraft inspection program approved under 14 CFR Part 135, Section 135.419, and currently in use by a person holding an operating certificate issued under 14 CFR Part 135. 3. A current inspection program recommended by the manufacturer. 4. Any other inspection program established by the registered owner or operator of the airplane or turbine-powered rotorcraft and approved by the FAA. This program must be submitted to the local FAA FS2 having jurisdiction of the area in which the aircraft is based. The program must be in writing and include at least the following information: instructions and procedures for the conduct of inspections for the particular make and model airplane or turbine-powered rotorcraft, including the necessary tests and checks. The instructions and procedures must set forth and detail the parts and areas of the airframe, engines, propellers, rotors, and appliances, including survival and emergency equipment, required to be inspected. A schedule for performing the inspections that must be performed under the program expressed in terms of the time and service, calendar time, number of system operation cycles, or any combination of these. 261. This FAA-approved owner/operator program can be revised at a future date by the FAA, if they find that revisions are necessary for the continued adequacy of the program. The owner/operator can petition the FAA within 30 days of notification to reconsider the notice to make changes. Manufacturer's Inspection Program. This is a program developed by the manufacturer for their product. It is contained in the instructions for continued airworthiness required under 14 CFR Part 23, Section 23.1529 and Part 25, Section 25.1529. It is in the form of a manual, or manuals as appropriate, for the quantity of data to be provided and including, but not limited to, the following content: a description of the airplane and its systems and installations, including its engines, propellers, and appliances. Basic information describing how the airplane components and systems are controlled and operated, including any special procedures and limitations that apply. Servicing information that covers servicing points, capacities of tanks, reservoirs, types of fluids to be used, pressures applicable to the various systems, lubrication points, lubricants to be used, equipment required for servicing, tow instructions, mooring, jacking, and leveling information. Maintenance instructions with scheduling information for the airplane and each component that provides the recommended periods at which they should be cleaned, inspected, adjusted, tested, and lubricated, and the degree of inspection and work recommended at these periods. The recommended overhaul periods and necessary cross-references to the airworthiness limitations section of the manual. The inspection program that details the frequency and extent of the inspections necessary to provide for the continued airworthiness of the airplane. Diagrams of structural access plates and information needed to gain access for inspections when access plates are not provided. Details for the application of special inspection techniques, including radiographic and ultrasonic testing where such processes are specified. A list of special tools needed. An airworthiness limitations section that is segregated and clearly distinguishable from the rest of the document. This section must set forth 1. Each mandatory replacement time, structural inspection interval, and related structural inspection procedures required for type certification, or approved under 14 CFR Part 23 or Part 25. 2. Each mandatory replacement time, inspection interval, related inspection procedure, and all critical design configuration control limitations approved under 14 CFR Part 23 or Part 25, for the fuel tank system. The airworthiness limitations section must contain a legible statement in a prominent location that reads: the airworthiness limitations section is FAA approved, and specifies maintenance required under 14 CFR Part 43, Sections 43.16 and Part 91, Section 91.403, unless an alternative program has been FAA approved. Any operator who wishes to adopt the manufacturer's inspection program should first contact their local FAA Flight Standards District Office for further guidance. Altimeter and static system inspections in accordance with 4 CFR Part 91, Section 91.411. Any person operating an airplane or helicopter in controlled airspace under Instrument Flight Rules IFR must have had, within the preceding 24 calendar months, each static pressure system, each altimeter instrument, and each automatic pressure altitude reporting system tested and inspected and found to comply with 14 CFR Part 43, Appendix E. Those test and inspections must be conducted by appropriately rated persons under 14 CFR. Air Traffic Control ATC Transponder Inspections. Any person using an air traffic control ATC transponder must have had, within the preceding 24 calendar months, that transponder tested and inspected and found to comply with 14 CFR Part 43, Appendix F, and Part 91, Section 91.411. Additionally, following any installation or maintenance on an ATC transponder where data correspondence error could be introduced, the integrated system must be tested and inspected and found to comply with 14 CFR Part 43, Appendix E, and Part 91, Section 91.411 by an appropriately person under 14 CFR. Emergency Locator Transmitter ELD operational and maintenance practices in accordance with Advisory Circular AC 9144. This AC combined and updated several ACs on the subject of ELDs and receivers for airborne service. Under the operating rules of 14 CFR Part 91, most small U.S. registered civil airplanes equipped to carry more than one 262 person must have an ELD attached to the airplane. 14 CFR Part 91, Section 91.207 defines the requirements of a type aircraft and when the ELD must be installed. It also states that an ELD that meets the requirements of Technical Standard Order OC 91 may not be used for new installations. The pilot in command of an aircraft equipped with an ELD is responsible for its operation and, prior to engine shutdown at the end of each flight, should tune the VHF receiver to 121.5 MHz and listen for ELD activations. Maintenance personnel are responsible for accidental activation during the actual period of their work. Maintenance of ELDs is subject to 14 CFR Part 43 and Part 91, Section 91.413 and should be included in the required inspections. It is essential that the impact switch operation and the transmitter output be checked using the manufacturer's instructions. testing of an ELT prior to installation, or for maintenance reasons, should be conducted in a metal enclosure in order to avoid outside radiation by the transmitter. If this is not possible, the test should be conducted only within the first 5 minutes after any hour. Manufacturers of ELTs are required to mark the expiration date of the battery, based on 50% of the useful life, on the outside of the transmitter. The batteries are required to be replaced on that date, or when the transmitter has been in use for more than 1 cumulative hour. Water-activated batteries have virtually unlimited shelf life. They are not usually marked with an expiration date. They must be replaced after activation regardless of how long they were in service. The battery replacement can be accomplished by a pilot on a portable type ELT that is readily accessible and can be removed and reinstalled in the aircraft by a simple operation. That would be considered preventive maintenance under 14 CFR Part 43, Section 43.3g. Replacement batteries should be approved for the specific model of ELT, and the installation performed in accordance with Section 43.13. AC 9144 also contains additional information on airborne homing and alerting equipment for use with ELTs. Search and rescue responsibility. Alert and search procedures including various flight procedures for locating an ELT. The FAA frequency management offices for contacting by manufacturers when they are demonstrating and testing ELTs. Although there is no regulatory requirement to install a 406 ELT, the benefits are numerous, regardless of regulatory minimums. All new installations must be a 406 MHz digital ELT. It must meet the standards of SOC 126. When installed, the new 406 MHz ELT should be registered, so that if the aircraft were to go down, search and rescue could take full advantage of the benefits the system offers. The digital circuitry of the 406 ELT can be coded with information about the aircraft type, base location, ownership, etc. This coding allows the search and rescue SAR coordinating centers to contact the registered owner or operator if a signal is detected to determine if the aircraft is flying or parked. This type of identification permits a rapid SAR response in the event of an accident, and will save valuable resources from a false alarm search. Annual and 100-hour inspections. Preparation. An owner/operator bringing an aircraft into a maintenance facility for an annual or 100-hour inspection may not know what is involved in the process. This is the point at which the person who performs the inspection sits down with the customer to review the records and discuss any maintenance issues, repairs needed, or additional work the customer may want done. Moreover, the time spent on these items before starting the inspection usually saves time and money before the work is completed. The work order describes the work that will be performed and the fee that the owner pays for the service. It is a contract that includes the parts, materials, and labor to complete the inspection. It may also include additional maintenance and repairs requested by the owner or found during the inspection. Additional materials such as ADs, manufacturer service bulletins and letters, and vendor service information must be researched to include the avionics and emergency equipment on the aircraft. The TCDS provides all the components eligible for installation on the aircraft. The review of the aircraft records is one of the most important parts of any inspection. Those records provide the history of the aircraft. The records to be kept, and how they are to be maintained, are listed in 14 CFR Part 91, Section 91.417. Among those records that must be tracked are records of maintenance, preventive maintenance, and alteration, records of the last 100-hour, annual, or other required or approved inspections for the airframe, engine propeller, rotor, and appliances of an aircraft. The records must include a description or reference to data acceptable to the FAA of the work performed, the date of completion of the work performed, and the signature and certificate number of the person approving the aircraft for return to service. 263. The total time in service and the current status of life-limited parts of the airframe, each engine, each propeller, and each rotor. The time since last overhaul of all items installed on the aircraft which are required to be overhauled on the specified time basis. The current inspection status of the aircraft, including the time since last inspection required by the program under which the aircraft and its appliances are maintained. The current status of applicable ADs including for each, the method of compliance, the AD number, and revision date. If the AD involves recurring action, the time and date when the next action is required. Copies of the forms prescribed by 14 CFR Part 43, Section 43.9, for each major alteration to the airframe and currently installed components. The owner/operator is required to retain the records of inspection until the work is repeated, or for 1 year after the work is performed. Most of the other records, that include total times and current status of life-limited parts, overhaul times, and AD status must be retained and transferred with the aircraft when it is sold. 14 CFR Part 43, Part 43.15, requires that each person performing a 100-hour or annual inspection shall use a checklist while performing the inspection. The The checklist may be one developed by the person, one provided by the manufacturer of the equipment being inspected, or one obtained from another source. The checklist must include the scope and detail of the items contained in Part 43, Appendix D. The inspection checklist provided by the manufacturer is the preferred one to use. The manufacturer separates the areas to inspect such as engine, cabin, wing, empennage, and landing gear. They typically list service bulletins and service letters for specific areas of the aircraft and the appliances that are installed. Initial run-up provides an assessment to the condition of the engine prior to performing the inspection. The run-up should include full power and idle RPM, magneto operation, including positive switch grounding, fuel mixture check, oil and fuel pressure, and cylinder head and oil temperatures. After the engine run, check it for fuel, oil, and hydraulic leaks. Following the checklist, the entire aircraft shall be opened by removing all necessary inspection plates, access doors, fairings, and cowling. The entire aircraft must then be cleaned to uncover hidden cracks or defects that may have been missed because of the dirt. Following in order and using the checklist, visually inspect each item, or perform the checks or tests necessary to verify the condition of the component or system. Record discrepancies when they are found. The entire aircraft should be inspected, and a list of discrepancies be presented to the owner. A typical inspection following a checklist on a small single-engine airplane may include in part, as applicable, the fuselage for damage, corrosion, and attachment of fittings, antennas, and lights, for smoking rivets especially in the landing gear area indicating the possibility of structural movement or hidden failure. The flight deck and cabin area for loose equipment that could foul the controls, seats and seatbelts for defects, windows and windshields for deterioration, instruments for condition, markings, and operation, flight and engine controls for proper operation, the engine and attached components for visual evidence of leaks, studs and nuts for improper torque and obvious defects, engine mount and vibration dampeners for cracks, deterioration, and looseness, engine controls for defects, operation, and safetying, the internal engine for cylinder compression, spark plugs for operation, oil screens and filters for metal particles or foreign matter, exhaust stacks and mufflers for leaks, cracks, and missing hardware, cooling baffles for deterioration, damage, and missing seals, and engine cowling for cracks and defects. The landing gear group for condition and attachment, shock absorbing devices for leaks and fluid levels, retracting and locking mechanism for defects, damage, and operation, hydraulic lines for leakage, electrical system for chafing, and switches for operation, wheels and bearings for condition, tires for wear and cuts, and brakes for condition and adjustment. The wing and center section assembly for condition, skin deterioration, distortion, structural failure, and attachment. The empennage assembly for condition, distortion, skin deterioration, evidence of failure, smoking rivets, secure attachment, and component operation and installation. The propeller group and system components for torque and proper safetying, the propeller for nicks, cracks, and oil leaks, the anti-icing devices for defects and operation, and the control mechanism for operation, mounting, and restricted movement. The radios and electronic equipment for improper installation and mounting, wiring and conduits for improper routing, insecure mounting, and obvious. 264. Defects, bonding and shielding for installation and condition, and all antennas for condition, mounting, and operation. Additionally, if not already inspected and serviced, the main battery inspected for condition, mounting, corrosion, and electrical charge. Any and all installed miscellaneous items and components that are not otherwise covered by this listing for condition and operation. With the aircraft inspection checklist completed, the list of discrepancies should be transferred to the work order. As part of the annual and 100-hour inspections, the engine oil is drained and replaced because new filters and slasher clean screens have been installed in the engine. The repairs are then completed and all fluid systems serviced. Before approving the aircraft for return to service after the annual or 100-hour inspection, 14 CFR states that the engine must be run to determine satisfactory performance in accordance with the manufacturer's recommendations. The run must include power output static and idle RPM, magnetos for drop and switch ground, fuel and oil pressure, cylinder and oil temperature. After the run, the engine is inspected for fluid leaks and the oil level is checked a final time before close-up of the cowling. With the aircraft inspection completed, all inspections plates, access doors, fairing and cowling that were removed must be reinstalled. It is a good practice to visually check inside the inspection areas for tools, shop racks, etc. prior to close-up. Using the checklist and discrepancy list to review areas that were repaired will help ensure the aircraft is properly returned to service. Upon completion of the inspection, the records for each airframe, engine, propeller, and appliance must be signed off. The record entry in accordance with 14 CFR Part 43, Section 43.11 must include the following information: the type inspection and a brief description of the extent of the inspection, the date of the inspection and aircraft total time and service, the signature, the certificate number, and kind of certificate held by the person approving or disapproving for return to service the aircraft, airframe, aircraft engine, propeller, appliance, component part, or portions thereof. For the annual and 100-hour inspection, if the aircraft is found to be airworthy and approved for return to service, enter the following statement. I certify that this aircraft has been inspected in accordance with the insert type inspection and was determined to be in airworthy condition. If the aircraft is not approved for return to service because of necessary maintenance, non-compliance with applicable specifications, airworthiness directives, or other approved data, enter the following statement. I certify that this aircraft has been inspected in accordance with the insert type inspection, and a list of discrepancies and unairworthy items has been provided to the aircraft owner or operator. If the owner or operator did not want the discrepancies and or unairworthy items repaired at the location where the inspection was accomplished, they may have the option of flying the aircraft to another location with a special flight permit ferry permit. An application for a special flight permit can be made at the local FAA FS2. Other aircraft inspection and maintenance programs. Aircraft operating under 14 CFR Part 135, commuter and on demand, have additional rules for maintenance that must be followed beyond those in 14 CFR Parts 43 and 91. 14 CFR Part 135, Section 135.411 describes the applicable sections for maintaining aircraft that are type certificated for a passenger seating configuration, excluding any pilot seat, of 9 seats or less, and which sections are applicable to maintaining aircraft with 10 or more passenger seats. The following sections apply to aircraft with 9 seats or less. Section 135.415 requires each certificate holder to submit a service difficulty report whenever they have an occurrence, failure, malfunction, or defect in an aircraft concerning the list detailed in this section of the regulation. Section 135.417 requires each certificate holder to mail or deliver a mechanical interruption report for occurrences in multi-engine aircraft concerning unscheduled flight interruptions and the number of propeller featherings in flight, as detailed in this section of the regulation. Section 135.421 requires each certificate holder to comply with the manufacturer's recommended maintenance programs, or a program approved by the FAA for each aircraft, engine, propeller, rotor, and each item of emergency required by 14 CFR Part 135. This section also details requirements for single-engine IFR passenger carrying operations. 265. Section 135.422. This section applies to multi-engine airplanes and details requirements for aging airplane inspections and records review. It excludes airplanes in schedule operations between any point within the state of Alaska. Any certificated operator using aircraft with 10 or more passenger seats must have the required organization and maintenance programs, along with competent and knowledgeable people, to ensure a safe operation. Title 14 of the CFR, Sections 135.423 through 135.443 are numerous and complex, and compliance is required. However, they are not summarized in this handbook. It is the responsibility of the certificated operator to know and comply with these and all other applicable requirements of 14 CFR, and they should contact their local FAA FS2 for further guidance. The Approved Aircraft Inspection Program (AIP) is an FAA-approved inspection program for aircraft of 9 or less passenger seats operated under 14 CFR Part 135. The AIP is an operator-developed program tailored to their particular needs to satisfy aircraft inspection requirements. This program allows operators to develop procedures and time intervals for the accomplishment of inspection tasks in accordance with the needs of the aircraft, rather than repeat all the tasks at each 100-hour interval. The operator is responsible for the AIP. The program must encompass the total aircraft, including all avionics equipment, emergency equipment, cargo provisions, etc. FAA Advisory Circular 13510 as revised provides detailed guidance to develop an approved aircraft inspection program. The following is a summary, in part, of elements that the program should include. A schedule of individual tasks, inspections or groups of tasks, as well as the frequency for performing those tasks. Work forms designating those tasks with a sign-off provision for each. The forms may be developed by the operator or obtained from another source. Instructions for accomplishing each task. These tasks must satisfy 14 CFR Part 43, Section 43.13 regarding methods, techniques, practices, tools, and equipment. The instructions should include adequate information in a form suitable for use by the person performing the work. Provisions for operator-developed revisions to referenced instructions should be incorporated in the operator's manual. A system for recording discrepancies and their correction. A means for accounting for work forms upon completion of the inspection. These forms are used to satisfy the requirements of 14 CFR Part 91, Section 91.417, so they must be complete, legible, and identifiable as to the aircraft, and specific inspection to which they relate. Accommodation for variations in equipment and configurations between aircraft in the fleet. Provisions for transferring an aircraft from another program to the IAB. The development of the IAB may come from one of the following sources. An adoption of an aircraft manufacturer's inspection in its entirety. However, many aircraft manufacturers' programs do not encompass avionics, emergency equipment, appliances, and related installations that must be incorporated into the IAB. The inspection of these items and systems will require additions to the program to ensure they comply with the air carrier's operation specifications and is applicable to 14 CFR. A modified manufacturer's program. The operator may modify a manufacturer's inspection program to suit its needs. Modifications should be clearly identified and provide an equivalent level of safety to those in the manufacturer's approved program. An operator-developed program. This type of program is developed in its entirety by the operator. It should include methods, techniques, practices, and standards necessary for proper accomplishment of the program. An existing progressive inspection program 14 CFR Part 91.409D may be used as a basis for the development of an IAB. As part of this inspection program, the FAA strongly recommends that a corrosion protection control program and a supplemental structural inspection type program be included. A program revision procedure should be included, so that an evaluation of any revision can be made by the operator prior to submitting them to the FAA for approval. Procedures for administering the program should be established. These should include defining the duties and responsibilities for all personnel involved in the program, scheduling inspections, recording their accomplishment, and maintaining a file of completed work forms. The operator's manual should include a section that clearly describes the complete program, including procedures. 266. For program scheduling, recording, and accountability for continuing accomplishment of the program. This section serves to facilitate administration of the program by the certificate holder and to direct its accomplishment by mechanics or repair stations. The operator's manual should include instructions to accomplish the maintenance/inspection tasks. It should also contain a list of the necessary tools and equipment needed to perform the maintenance and inspections. The FAA FS2 will provide each operator with computer-generated operations specifications when they approve the program. Continuous Airworthiness Maintenance Program CAMP. The definition of maintenance in 14 CFR Part 1 includes inspection. The inspection program required for 14 CFR Part 121 and Part 135 air carriers is part of the Continuous Airworthiness Maintenance Program CAMP. CAMP is not required of every Part 135 carrier, it depends on aircraft being operated. It is a complex program that requires an organization of experienced and knowledgeable aviation personnel to implement it. The FAA has developed an advisory circular, AC 12016 as revised air carrier maintenance programs, which explains the background as well as the FAA regulatory requirements for these programs. The AC applies to air carriers subject to 14 CFR Parts 119, 121, and 135. For Part 135, it applies only to aircraft type certificated with 10 or more passenger seats. Any person wanting to place their aircraft on this type of program should contact their local FAA FS2 for guidance. Title 14 CFR Part 125, Section 125.247, Inspection Programs and Maintenance. This regulation applies to airplanes having a seating capacity of 20 or more passengers, or a maximum payload capacity of 6,000 pounds or more, when the aircraft is not required to be operated under 14 CFR Parts 121, 129, 135, and 137. Inspection programs which may be approved for use under this 14 CFR part include, but are not limited to, 1. A continuous inspection program which is part of a current continuous airworthiness program approved for use by a certificate holder under 14 CFR Part 121 or Part 135. 2. Inspection programs currently recommended by the manufacturer of the airplane, airplane engines, propellers, appliances, or survival and emergency equipment, or 3. An inspection program developed by a certificate holder under 14 CFR Part 125. The airplane subject to this part may not be operated unless the replacement times for life-limited parts specified in the aircraft type certificate data sheets, or other documents approved by the FAA are complied with, defects disclosed between inspections, or as a result of inspection, have been corrected in accordance with 14 CFR Part 43, and the airplane, including airframe, aircraft engines, propellers, appliances, and survival and emergency equipment, and their component parts, is inspected in accordance with an inspection program approved by the FAA. These inspections must include at least the following: instructions, procedures and standards for the particular make and model of airplane, including tests and checks. The instructions and procedures must set forth and detail the parts and areas of the airframe, aircraft engines, propellers, appliances, and survival and emergency equipment required to be inspected. A schedule for the performance of the inspections that must be performed under the program, expressed in terms of the time and service, calendar time, number of system operations, or any combination of these. The person used to perform the inspections required by 14 CFR Part 125 must be authorized to perform maintenance under 14 CFR Part 43. The airplane subject to Part 125 may not be operated unless the installed engines have been maintained in accordance with the overhaul periods recommended by the manufacturer or a program approved by the FAA. The engine overhaul periods are specified in the inspection programs required by 14 CFR Part 125, Section 125.247. Helicopter inspections, piston engine and turbine powered. A piston engine helicopter must be inspected in accordance with the scope and detail of 14 CFR Part 43, Appendix D for an annual inspection. However, there are additional performance rules for inspections under 14 CFR Part 43, 267. Section 43.15, requiring that each person performing an inspection under 14 CFR Part 91 on the rotorcraft shall inspect these additional components in accordance with the maintenance manual or instructions for continued airworthiness of the manufacturer concerned. 1. The drive shaft or similar systems. 2. The main rotor transmission gearbox for obvious defects. 3. The main rotor and center section or the equivalent area. 4. The auxiliary rotor. The operator of a turbine-powered helicopter can elect to have it inspected under 14 CFR Part 91, Section 91.409. 1. Annual inspection. 2. 100-hour inspection, when being used for compensation or hire. 3. A progressive inspection, when authorized by the FAA. 4. An inspection program listed under 14 CFR Part 91, Section 91.409F, and selected by the owner/operator, and the selection is recorded in the Aircraft Maintenance Records 14 CFR Part 91, Section 91.409E. When performing any of the above inspections, the additional performance rules under 14 CFR Part 43, Section 43.15, for rotorcraft must be complied with. Light sport aircraft and aircraft certificated as experimental. Light sport aircraft and aircraft that are certificated in the experimental category are issued a special airworthiness certificate by the FAA. Operating limitations are issued to these aircraft as a part of the special airworthiness certificate that specify the required inspections and inspection intervals for the aircraft. Typically, the operating limitations issued to these aircraft require that a condition inspection be performed once every 12 months. If the aircraft is used for compensation or hire, e.g., towing a glider, flight training, then it must also be inspected each 100 hours. A condition inspection is equivalent to the scope and detail of an annual inspection, the requirements of which are outlined in 14 CFR Part 43, Appendix D. An A&P or an appropriately rated repair station can perform the condition inspection on any of these aircraft. The FAA issues repairman certificates to individuals who are the builder of an amateur-built aircraft, which authorizes performance of the condition inspection. Additionally, repairman certificates can be issued to individuals for conducting inspections on light sport aircraft. There are 2 ratings available for Light Sport Repairman Certificate, each with different privileges as described in 14 CFR Part 65, Section 65.107, but both ratings authorize the repairman to conduct the annual condition inspection. The operating limitations issued to the aircraft also require that the condition inspection be recorded in the aircraft maintenance records. The following or similarly worded statement is used. I certify that this aircraft has been inspected on insert date per the insert either scope and detail of 14 CFR Part 43, Appendix D, or manufacturer's inspection procedures, and was found to be in a condition for safe operation. The entry will include the aircraft's total time and service cycles if appropriate, and the name, signature, certificate number, and type of certificate held by the person performing the inspection. 268. Chapter 3. Aircraft Fabric Covering. General History.